Hi everybody, this is Mr. Folly, and we are back into more of the mole unit, and we get to cruise along into podcast 4.3. Here we have the fun, very, very heavy math chapter, so make sure you have your calculator and your periodic table handy for this. We're going to do percent composition and percent. It drives me nuts that we spend any time at all on percent, but we always do. Percent, as always, is just part over total times 100%. And there's no change to that. The percent of your grade, the percent composition, the percent that you made money in the stock market. Then we have empirical formulae. This is the plural formula, just to be fancy pants. Molecular formulae, which is always fun. And you don't know what those are yet, but I'm sure you can't wait. So let's go ahead and get started. Percent composition. Compounds are made of elements in different ratios. So if we want to find the percent nitrogen in NH3, remember this formula is constant. So I can choose any amount that I want, and guess what amount I choose? Always go through moles, always go through moles, always go through moles. So N in NH3, N is 14.01, and then NH3 is 14.01 plus 3.03. How sad is it? I'm using my calculator for this. It's 17.04. And then times 100%. So 14.01 divided by 17.04 will give me 82.2%. Find the percent H in NH3 would be simply 3.03 over 17.04 times 100%. Or you can simply take 100 minus 82.2, and you would get 17.8%. Either way works. Make sure you show your work, though. Don't just write something down. Find the percent composition of ammonium nitrate. So again, we're dealing with having to be able to come up with a formula. Ammonium is NH4 plus 1. Nitrate is NO3 minus 1. Excuse me. So if it says find the percent composition, that means you have to do for each part. So let's do N first. I have two nitrogens. So nitrogen is 28.02. Hydrogen, I have four of them, is 4.04. Oxygen, there's three of them. 16 times 3 is 48. And then if I want to find the percent composition of each of these, I would take my 28.02 over the total, which is 28.02 plus 4.04 plus 48, which is 80.06. I just want to say again that I include my 82.02 in my total. So make sure you have that included in it. So 28.02 divided by my answer gives me 35.0%. And really I should have 4 sig figs because I've got 4 sig figs for this, so it should be 35.00%. Nitrogen. Then for hydrogen, it's 4.04 divided by 80.06. And I got 0.05. Now I didn't show my times 100, but I'm moving the decimal. And I get 0.05, and that's going to be 5.046%. Again, 4 sig figs because that's what I had coming into it. Oxygen is going to be 48 over 80.06, and then of course times 100. 48 divided by 80.06 is 59.96. And then make sure I label which one's which to make life much easier. If I have a sample of ammonium nitrate that has 33.55 grams of hydrogen in it, how big is the sample? So again, remember, percent is just part over total equals percent. And then I just kind of move the decimal on its own there. So if I have 3.55 grams of hydrogen, that means my part is 3.55 grams, right? My total is what I'm looking for. And I know that my percentage of hydrogen is, notice I'm kind of factoring in that times 100, 0.05046. So that means to solve for the total, I have to cross multiply and get it over here. So, and then cross multiply this and get it down there. So I have 3.55 over 0.05046 equals my total mass. So my total mass equals 3.55 divided by 0.05046, which is 70.35 grams. That's the other trick I can do to you, is if you have a given percent, you can be given part and figure out the mass that goes with it. Next slide, please. If I have 35 grams of NH4NO3, how many grams of oxygen would I have? So again, it's going to be part over total equals percent. So my part is what I'm solving for. My total was 35 grams. And I've forgotten my percent of oxygen, so I'm going to go back and look. 59.96 is my percent of oxygen. So 0.5996. So for this one, I'm going to cross multiply, and all I have to do is 0.5996 times 35. So 0.5996 times 35 gives me 20.99 grams of oxygen. Now we're going to move on to empirical formula. An empirical formula is the reduced formula. So C6H12 has an empirical formula of CH2. So I would divide both of those by 6, and I would get CH2. Water's molecular formula is H2O. What is its empirical formula? It's the same. Water's exact formula is H2O. You can't reduce it. Okay. Now, if I had something like C2H3O4, I cannot reduce 2 and 4 because 3 does not have a common factor. So if you're just asking to do the reducing part, that's where that comes in. This means we need to find subscripts. So empirical formula is the reduced formula. So for example, we need to find the 2 in the H2O and also the 1 in the H2O. Subscripts represent atoms. Remember I say water looks like Mickey Mouse. And it's H2O because this has one O right there. And the H's are the ears. Okay. And we group atoms in moles, so basically what we're going to do is we're going to take our masses, turn them into moles, and then make them small whole numbers, which is what the next slide says. How to find an empirical formula. Convert grams to moles. Always go through moles. Get moles into whole numbers, so you're going to divide them by the smallest. If you divide by the smallest thing, you're guaranteed that you're going to have the numbers 1 or bigger. Multiply 2 or 3 if needed to get whole numbers. I'm not a huge fan of listing the steps. I'm a huge fan of just doing something 1,000 times, and then it starts to become easier. A substance is 58.266% iron and 41.734% oxygen. Find the empirical formula. Now, if I have percent compositions, I can assume any mass that I want to. So because I have percent, and cent means 100, what I'm going to do without even thinking about it is change these numbers from percents to grams. Now, I know you could move the decimal 2 places, but I don't like to do that. I like to use numbers bigger than 1. Why? I don't know. So I'm going to take 58.266 grams of iron, which is Fe, and 41.734 grams of oxygen, which is O, times dividing bar. Grams of Fe on the bottom, and all I'm doing is converting into moles. 1 mole on top. Little g stands for grams, and little g stands for go to the periodic table. So I'm going to take 58.266 divided by 55.85, and I get, whoops, I forgot to put 55.85 down here. And I get 1.0433 times dividing bar, grams of oxygen, 1 mole of oxygen. Now, because it's O, this is going to be Fe something, O something. I don't use 32 here because I have 1. I want to know how many oxygens I have, not how many O2s I have. So this is 16.00. So 2.734 divided by 16 is 2.6084. Now, oops, I should not have put that there. So what I want to do now is I've got these both in moles, and I need to get them into whole numbers. So to get them into whole numbers, I'm going to divide them both by the smallest one. And the smallest number is 1.0433. And see what I get. So 1.0433 divided by 1.0433 is 1. That's no surprise to anyone. And then 2.608 blah, blah, blah divided by 1.0433 hopefully will be a whole number, but it's not. It's 2.500. And let me just pause. Okay, so that's 2.500. Now I want these to be whole numbers. So what I'm going to do next, since 2.500 is very nearly a fractional number, I can multiply both of these by 2. Now why do I multiply it by 2? If I multiply 2.50 times 2, I would get the whole number 5. And 1 times 2 is 2, which is also a whole number. Okay, does that make some sense, I hope? So the fractions you need to be able to identify off the top of your head are 0.5 is a half, you'd multiply it by 2, 0.33 a third, multiply it by 2, and 0.666 2/3, you'd multiply by 3. I think I said well, this you'd multiply by 3, this you'd multiply by 3, because you're talking about thirds. This you'd multiply by 2, because you're talking about halves. So now let's get the answer here. This 2 goes with FE, so I have FE2. This 5 goes with O, FE2O5. There's my thing. And this is the hardest that I can make it because you had the extra multiply it by something step. Let's take a look at another one. Compound is 40% carbon, 53.29% oxygen, and 6.714% hydrogen. Find the empirical formula. So again, I just changed it into grams. So 40.00 grams of carbon, 53.29 grams of oxygen, and 6.714 grams of hydrogen. First step, always go through moles. So grams on the bottom, 1 mole on top. 12.01 is carbon from the periodic table. Little g stands for grams. Little g stands for go to the periodic table. 16 grams of oxygen is 1 mole. And 1.01 grams of hydrogen and 1 mole. So do this happy math. So 40 divided by 12.01 is 3.33. And you might already be thinking this is going to be a third, but it's probably not going to be because I'm going to have to divide by the smallest number. So 53.29 divided by 16 is also 3.33. So that tells me that the carbon and hydrogen will probably have the same subscript. And 6.714 divided by 1.01 will be 6.648. Okay, and then remember the next step is to divide by the smallest, because we want to make these things be whole numbers. So if I divide by the smallest, again, what I'm going to get is everything's going to be at least 1. So if you want things to be a whole number, you want them to be 1 or larger. Bottom or the top 2 are 1, and then 6.648. This is going to be 2, divided by 3.331, and I get 1.995. That's 2. Okay. So this means my answer, I don't have to do that next step at all. So my answer is, that's carbon, that's oxygen, that's hydrogen. So it's simply H2O. Most of the time the H is coming before the O's. I'm sorry I did that. So it would be OH2 is perfectly acceptable. I'm sorry, I got all weird on the other one. All right. Another one? Yes, another one. Here I've got just plain old grams. Okay? So it doesn't matter if you're in grams or not. You use your grams. Remember, the first thing we did if we had percentages would turn them into grams. So I'm going to pause for the announcements. Okay, now that I've said the Pledge of Allegiance, we have 75 grams of carbon and 25 grams of hydrogen. And in case you haven't noticed, I've done my typical thing of do the toughest problem first. So hopefully you're finding this easier as we go. So again, remember the first step is go through moles. Always go through moles. So I hate grams of carbon, and 1 mole of carbon goes on top. Little g stands for grams, and little g stands for go to the periodic table. Same thing for hydrogen. Hating grams of hydrogen, put grams of hydrogen on the bottom. 1 mole of hydrogen on top. So again, I hated grams of carbon, so I cancel it. So grams of carbon is 1.01 gram of hydrogen, from the periodic table again. And again, because H is going to be attached to C, it is not diatomic, so I don't use that double weight. So 75 divided by 12.01 is 6.244, or 6.245. And then 25 divided by 1.01 is 24.75. 2. Divide by the smallest. And this, again, the point is to get numbers of 1 or bigger, and as small whole numbers as possible. So 6.245 divided by 6.245. This is going to be exactly 1, and this is going to be probably exactly 4, but let's check it out. Divided by 6.245, and I get 3.96. Ooh, decision time. 3.96. Is that 4 or is that 3.66? Those are your choices. You better pick that's 4. Okay. So that means that my answer is going to be C1H4. That's it. I'll have another one of those to do. Molecular formulas are exact formulas. Water is H2O. You know, water looks like Mickey Mouse. There's no kind of fancy pants reduction there. Hydrogen peroxide is H2O2. So that looks not like Mickey Mouse, but like that. Sugar is C6H12O6. These are the actual formulas. Notice they're not reduced. That's the actual formulas. That's what it actually looks like. Sometimes you care that you have equal ratios of arms and legs. You know, the ratios sometimes matter. It makes it simpler. Sometimes it actually matters that you have 10 fingers. Exactly 10. You don't reduce your hand to 1 thumb and 1 finger. You don't reduce that. A lot of times it really matters that you have 4 fingers on each hand and 1 thumb on each hand. Finding a molecular formula. Molecular mass is the mass of the exact molecule. That's given. That's almost always given. And I'm going to say it's always given. Find the empirical formula mass by going to the periodic table. You may first need to find the empirical formula from all the stuff we just did. Use that as a multiplier, which seems weird right now. But let's say for an example, let's say my empirical formula is SO3. And then I figure out my multiplier is 4. I do the math, I figure out my multiplier is 4. So SO3 times 4 would be S4O12. So it looks like you're multiplying it and you'd put whatever it is. But that's what it is. Looking at that, it'll make more sense as well. Substance has an empirical formula CH2N and a molecular mass of 112.16. Find the molecular formula. So here's my empirical formula. And what I'm going to do is find the empirical mass of that. So carbon is 12.01. Hydrogen is 1.01, but I have 2 of them, 2.02. And nitrogen is 14.01. Where are these numbers coming from? I'm dealing with a mass, so grams means go to the periodic table. So my empirical mass equals 28.04. Now, my molecular mass is 112.16. Whoops, that's not a 6. 112.16. And that is the mass of my exact thing. I want to know how many CH2Ns fit in this big monstrosity of my molecular compound. So maybe it's 1, but it's not 28.06. Maybe it's 2, maybe it's 3. So if it was 1, it would be 28.04, and that would be my answer. If it was 2, it would be double this, 56.08. If it was 3, it would be 3 times 28.04, which is beyond my willingness to compute in my head. So what I'm going to do to solve for this bad boy is to take 112.16 and divide it by 28.04. And that will tell me how many reduced things fit in the exact one. Divided by 28.04. And I get exactly 4. So here my multiplier is 4. So my answer is going to be C4H8N4. Not too bad. Get your masses, get a whole number you're going to multiply by. It'll always be bigger. And go to town. An oxysulfur compound smells like rotten eggs and has a molecular mass of 48.1. Give the molecular formula. Oxysulfur means it's got 2 things in it, oxygen and sulfur. Has a molecular mass of 48.1. Now, I think this might not be enough information to do this. So what I'm going to do is I'm going to look and see if it's SO. Sulfur is 32.06. Oxygen is 16.00. That is 48.1. So that's if I have one of each. All right? So if I have one of each, that one sulfur and one oxygen would be 48.1, right, or 48.06. So that means the molecular formula is simply SO. Hopefully that works for everybody. You can see how that came up with that. Okay, oxysulfur means you've got oxygen and sulfur. If it would have, so this is one with each of them. If it would have been, say, 64, then it would have been SO2. So that's a mean one. Naturally conceptual one, but hopefully that works for you guys. Compound is, whoops, looks like I forgot to put the numbers in there. Yeah, that's missing something. So that's a problem we get to skip. Yay, that makes this podcast a whole lot faster. It should have had a percentage for each one of these in here, but apparently that didn't save when I put it in here. And since I'm already 22 minutes into it, we'll just go into here. Why do we care? Finding empirical and molecular formulas allows chemical engineers to design molecules and make life better. If you can determine the empirical formula, you know what elements are present. And that's half the battle if you want to build, say, a wonder drug. If you know the molecular formula, you know the number of each element present. So through different reactions and things like that, you can figure out some active groups, or what these things are called, or active sites. If you remember in biology, you had active sites where enzymes would interact and things like that. So the empirical formula tells you what elements and the ratios. The molecular formula tells you the exact number, and then chemical engineers can find the active sites for these different things. So let's say they find the cure for cancer is in a tree in Brazil. Okay, so cancer cure is in a tree in Brazil. So they find this chemical, and what they want to do, say you're a drug company, you find this chemical, you don't want to have to wait for trees to grow to cure cancer. Okay, that's a big issue. Trees take a long time to grow. So what you want to do is figure out what chemical cures cancer. So first you can find the empirical formula, then you find the molecular formula, and then you go to work on designing the chemical. Once you find out what the structure of the chemical is and figure out a way to make the chemical, then you can make it in a lab. Making something in a lab, now the first one takes years and years and years to make. So to figure out how to actually make it, say it takes 10 years. Which might be long, might be short, I'm not quite so sure about it. But 10 years for the cure for cancer probably wouldn't be too terrible if they found it in a tree in Brazil. It'd probably be less, but whatever. So now if you can make it in a lab, once you've that first one done, in the lab you can make thousands of pills per day. And what that means is you don't have to keep farming these dumb trees that nobody really cares about, right? So you don't have to farm these big dumb trees. We can cut down those trees and make something that people really care about, like Best Buys or whatever it is that you guys want to put up there. Okay. So why do we care this way? We can let science mass produce the cure for cancer, save more people, less people become, let me do this again, less people become dead. Oops, I guess that would be a frown. More people become alive. And then we can cut down trees and build houses and Best Buys and parks or whatever it is that we want. And that is it. And we're out of here in the happy, under 25-minute campaign. So, woohoo! Have a good one, and I'll see you in class tomorrow.